I will talk of not on what we can do with big data or what we have to be careful about, etc., like Julia did very nicely this morning, but rather on what does it need, what does it take materially to produce this big data, to analyze it, etc. So on what type of infrastructure does it rely on? And so, do you see my screen okay?
Yes, we do. Perfect.
Oh,
no, we don't.
Yep, I want
there we go.
to get in full screen mode. No, let me start again. Sorry. Hop, I will make it full screen first. And the talk will be mainly first with a little context on the crisis, climate crisis and ecological crisis, and then moving on to how we estimate the CO2 footprint. Yeah, okay, should be good now. CO2 footprint, and then what we can do about it. And it's a quite large collaborative work done with colleagues from various labs in Toulouse, in an institute that is doing astrophysics, meteorology, biosphere monitoring, oceanography, and geoscience. Okay, so you have all heard of the IPCC results, so I will just show this graph, but of course you know that we are on a period of rising global average temperature, and we have already made about a plus 1.2 degree changes. And when we compare this change, 1 degree may look small, but we are on the way for several degrees. And as it's stated in the summary, in the technical report of the last IPCC report, life on Earth is able to survive a major climate change, evolving to new species, but humankind is not. So clearly, climate change as it's unfolding is a threat, is an existential threat for our society. And there is not only the climate crisis, and you can look at this little cartoon here that was done during the COVID, because COVID was the major threat we were facing. But on the background, on the broader picture, there was the question of climate change and biodiversity collapse. And there is another group of experts that is summarizing the result about biodiversity, the IPBES. And when you look at its last report a few years ago, one very interesting finding is that, of course, there is a catastrophic, and I will not discuss it, loss of biodiversity in terms of species extinction, biomass of different species, etc. But what is interesting is that the cause of this biodiversity crisis is not much related to climate change. And it's estimated that climate change is responsible for only about 10%. So what you see here is the different causes or the drivers of the biodiversity decline. The major causes actually are direct human activities, either through land use or sea use changes, through direct exploitation, for example, in agricultural land by using various chemicals, or through other type of pollution. So when you think of this, it means that when we look to solution, or when we think about how our society, has to change to face the climate crisis and the biodiversity crisis, we should really have broad pictures and not focus on miracle solution or on solution that only address one part of the problem. And one interesting viewpoint is the viewpoint of planetary boundary, of the question of what part of the Earth system is disturbed beyond what is sustainable, let's say, by the human activities. And in this view, you have many different boundaries. Again, we can come back later, but clearly there is a question of climate change that is exceeded. The biodiversity is also at risk, but there are also other aspects like ozone depletion. This is fairly well known, and now it's under control, but over a question like excess or disturbance of the biogeochemical flows of phosphorus or nitrogen, or land system changes, etc. And therefore, when we think to carbon capture or to new ways to decarbonize the economy, we have to think that this will solve maybe the question for climate change if we would have a very large amount of carbon-free energy from fusion reactor, for example, nuclear fusion. But this would not really address the other question, like what would we do in terms of the pollution, novel entities, or in terms of biosphere degradation or land use changes. So we really need to think how to have solutions that do not increase the pressure on other boundaries. And in this talk now, I will focus on CO2 emission because it's the one that is the most advanced, but we should always keep in mind when we think to solution or to what we want to change, to have a goal that do not worsen the problem. And one also important aspect I want to add is that many people focus on the question of the fossil fuel industry with very good reason, because CO2 emission, you can see here the global CO2 emissions since 150 years are mainly driven by fossil fuel burning, so coal, oil, and gas, to some extent land use change. But when you look at energy consumption, what is important to realize is that we have only been adding different source of energy. We have been burning wood, and then we have added coal around 1900 or even before. And after that, we have added oil and gas, and then other source of energy like nuclear or the new renewable energy. But there's never been a transition. So when we think that we have to decarbonize, this is also really something that is historically, which has never been seen historically. And when we look at the order of magnitude of what we have to do, the last figures of the IPCC report are the most interesting. You have here again the global emission of CO2 equivalent in gigatons, or around 60 billions of tons. And what you see is that if we want to maintain the global climate below 2 degrees or below 1.5 degrees, we have to go to rapid reduction. And what is currently engaged by the promises or the engagement, the commitments of the different states in the last COP is actually only a stabilization of the emission, as before this was rather a rising curve. And this stabilization is leading us to a +3 degree world, which would have very severe consequences, especially in the global south, but also in the global north. And sorry, if you would want to meet the 1.5 agreement, we would need to have about a 10% per year reduction rate. And of course, this should affect all sectors, so that in 2050, we would have only a few tons of CO2 maybe per person if you would distribute them equally among 10 billion humans. So the question is how society will get in this transition, in this revolution, if you want, Evan, and what's the role of science into that, and where is science in this in terms of emission? One thing I won't detail there, but you can ask me question at the end, is that there is also the question about green growth, and that could be applied to society or to some extent to science. Can we grow and expand, but in the same time as growing GDP, for example, decrease CO2? Well, actually, some economists have studied that, and they found, looking at 40 high-income countries, that some countries have done that, but at a rate that is very, very insufficient. If you look at how CO2 emission here have decreased through the years between 2013 and 2020, the reduction is very, very far from what we would need to do to meet the Paris Agreement, so a 1.5 degree limit. So this is insufficient. Another point is that, well, if scientists also want to reduce their CO2 footprint and their CO2 emission, is it just because do we have to do more, or do we have a special role compared to the rest of society? And one important thing is that geoscientists, they are influential in the sense that they help to define the problem, they help to provide solution. And there have been several psychological studies that showed that if climate experts are proposing policies in terms of reduction of the CO2 emission, and these policies can be very different. It can be increased nuclear power, it can be increased renewable energy, it can be increased public transport, or implement some form of CO2 quota or CO2 tax. Systematically, they found that the public has a stronger support, this point here, to the different policies when the scientist or the expert is presented as a low energy lifestyle person. So basically, there is a question of exemplarity, and if science is able or not able to show some form of exemplarity, this will influence how the world and the recommendation of scientists in terms of policy, in terms of societal changes will develop. Okay, so the two questions I will now try to address, and to presenting various data from my work and from works of others, is the question of what are the magnitude of the different sources of CO2 emissions from scientific activity, from producing big data, from analyzing it, etc. And the second one is, well, when we have identified these sources, how can we reduce them to achieve a form of sufficiency? So that's the alternative to green growth. It's a question of like, what do we need in terms of minimum resources to perform science, and exemplarity, as I said, to be able to be a lever of action in the broader society. Okay, so there will be two parts, one on quantifying and one on strategy of reduction. And I will start with the state of the art for quantifying emissions. So the general concept when you try to estimate a carbon footprint or greenhouse gas emissions is that you look at what a company or an industry or here a laboratory of science or university is doing, and you can separate that into the direct activities, scope 1, that is directly owning vehicles or using electricity energy in the buildings. And then you have the scope 2, that is the energy you use from that others have used to produce or offer you some services or product. But then the most important is the scope 3. Scope 3 are the different activities upstream or downstream that are required for you to be active. It can be the use of different forms of transport, the fact that you have to consume goods, to buy equipment, the fact that you produce waste, etc. And all of this needs to be translated or into an equivalent of CO2 and of other greenhouse gas, like methanes or nitrous oxide. And to do that, usually, what we do is that we account or we estimate the activity. Let's say how much electricity is consumed in a building or how many kilometers you have flight by plane. And you multiply that by an emission factor. And this emission factor, if it's for electricity, will be in CO2. How much CO2 do you emit for a given kilowatt per hour? And this will depend, of course, of the type of plant, coal plant or nuclear reactor that has produced the electricity. And this gives you an amount of CO2, and that by aggregating this different amount, you can estimate a carbon footprint or a carbon budget. Okay, so in France, in the last few years, there's been a group that is called GES. It means GHG, greenhouse gas 1.5. And this is a group that try to quantify and to propose strategy to decarbonize the academic system in France. So it's a national group with scientists from every lab in France. And there is a series of papers, and they have a very nice website that you can go and look at. And they have developed a tool that you can use online. It's adapted to French data system, but there is an ongoing development to adapt it to other systems. And it allows to convert the different main sources of CO2 associated with a lab functioning. So here, of course, you have the basic building activity, electricity, how much electricity, heat, or refrigerant fluids you used per year that you can convert. You have then the home workplace commuting assessed by a poll where people have to declare if they go by bike, by bus, by a personal car, and how many kilometers they do. And then you have a very large large source here that is one dominant source is the question of missions, professional travels, and typically it's dominated by air travels. If you look at my lab, the Geoscience and Environment Lab in Toulouse, we are 240 staff members, including PhD and support staff. And there is about 800 missions that are done in 2019. There were a bit more than 800 missions. This is several millions of kilometers. And this represents about 600 tons of CO2. That is 2.5 tons of CO2 per person. Then you can look also at hotel accommodation. But another point that is most important one in many lab cases is the question of how much goods and service you have to purchase, so you have to buy. And each of these goods, they have a certain cost. But depending on their category, depending if you buy food, furniture, electronics, or metal, it will have a certain amount of CO2 associated based on the average from companies in Europe. And when you do that, you convert the financial budget of the lab, that is about 2 million euros per year. And it's buying IT equipment. It's also including repair services. but buying lab equipment, etc., disposable equipment sometimes. All of this is representative for about 3 tons. So when you sum all of this, that is kind of a classic budget. Also, the question of buying goods is fairly new. There are some work in review and there are a few works only in the literature. You reach something like 7.5 tons of CO2 per person per year, just for the professional activities. And as I was saying at the start, you have seen that in 2050, the average target that you can take is that people should have about 2 tons of CO2 per person. So we are already quite above that. But the question is, what about large outsourced research infrastructure? For example, computing centers that are out of your lab, or satellites or other infrastructure that are international, but that are used by the scientists. So that's where we can push a bit beyond the state of the art. And there have been some scientists in France also looking at making the carbon budget of a computing center. And they try to estimate how much CO2 was produced for building the server and the server environment, how much electricity was consumed by the server and the other IT equipment, the environment, and then how much CO2 was associated with the staff working at this center so that it's operational, typically mainly related to staff commuting. When you sum this, assuming most servers last for about 7 years and the French electricity mix, you find that 1 hour of CPU on a computing center is about 5 grams of CO2. So which means that 1 million hours of CO2 would be about 5 tons. But what is very important here is that this is for the electrical mix of France that is fairly low. Whereas if you would look at the United Kingdom or India or China, basically different countries will have mix that are more or less carbon intensive. And you can raise this number to rather 9, 12, or even almost 20 tons of CO2 per million hours of CPU. You can do the same exercise, and this was done by other colleagues, for storing data. So if you use a cloud in the US, for example, and you store 100 terabytes of data during 1 year, this would be about 1 ton in France, again, because the electricity mix is small and it's about half with production. But if you're in the United States, it would rather be 3 tons of CO2. Okay, so when you do that, you can assess how much this is for a whole lab. If you make a poll, for example, in your lab, and you estimate how many hours of CPU or how many stored data you do per year. And I give you some value here for some labs in France. In my lab, we estimated that annually there is about 4.5 million hours of CPU, that is about 20 tons. And when you divide it by the 200 person of the lab, it's relatively small, 0.1 tons of CO2. If you would be in UK or in China, or if you would send your jobs to another country, this could increase by a factor 2 or 3. In other labs, this can be in a smaller lab of meteorology where they do more modeling. It's about 11 million hours, which means 50 tons of CO2. And given the lab is smaller, you go up to 0.5 tons of CO2 per year just for this external computing. And it's approximately equal to all staff commuting during a year. And some labs do even more, like oceanography and climatology lab in Paris is doing about 35 million hours of CPU, so it's more than 160 tons, and it's about 1 ton of CO2 per person. So we can include that. I think I don't need to go more into detail with that. But then another question is like, okay, this is for modeling. And we have seen that if you are an experimentalist, maybe it's about buying machines. If you are doing field work, you have to account for the flights that you take. But what happens if you use very large data sets coming, for example, from satellites or from other large infrastructure of research? So here, there is 2 issues. The first one is to find the emission factor. And here I used, I've been following the work by Knut Leser, that is a colleague in Toulouse also, but an astrophysicist, and they have published a paper in Nature Astronomy where they have summarized the work from life cycle emission estimated for 2 European Space Agency missions. And they found that for a satellite, for example, you have an emission factor of about 50 tons of CO2 per kilo of payload at launch. And this relates mainly to the satellite elements construction, because this is usually heavy industry, transport of the different satellite components, and then launch from the rocket. You have also to account for the construction of the rocket launcher. And so for a given satellite, we can estimate its payload fairly easily from online data from the NASA or etc. And then multiplying it by 50 tons, we find a total CO2 emission. And if we account for the amortization for how long is lasting the mission, we can divide it by the time since launch until present to accommodate for the fact that a mission that has been lasting for very long has been used by more scientists. But then we have the question of how to assign the CO2 of let's say a Landsat, the Landsat satellite or the Landsat missions with the different Landsat versions. How do you assign CO2 from all these satellites to a specific lab or to a specific author? Given that we don't know how, for a computing center, you know how many hours you have performed on the center, you know how many terabytes you have stored on the cloud, but it's almost impossible to know how much data has been used by any scientist from these platforms because they are relatively freely distributed. So what we did is to look at the output, basically at how much scientific production is associated with different infrastructure or with a satellite. And we look at how many manuscript is published by the lab for a given infrastructure for a given period of time, let's say for the last 5 years. And we looked at how many manuscripts in the same period were published in the world and were using this satellite. And then to account for the fact that in one manuscript, you may not only have authors from the given lab, we account for the average author fraction. So how many authors in average were really from the given lab in this manuscript. When we do that, we find a share of attribution that allows to say that, for example, this or this lab is using 1% or is responsible for 1% of the science produced with this satellite. And there is a last term that is here, that is the share to science, that is to account for the fact that some satellites actually are not only used by scientists, so part of their CO2 emission should be attributed rather to the industry or to the government. And we do that especially for satellites that are general observation satellites that have open science, and we have information for the Sentinel mission, for example, on the fact that this share may be only 50 or 30%, between 30 and 50% is for science, and the rest would be for other users. Okay, so then I used the Web of Science database to automatically extract the number of manuscripts. This extraction is based on abstract, title, and keywords. So it's not all the manuscripts using the satellite, but the ratio when we look at how many articles were published in the world with this method and how many articles were published by my lab, let's say, we can find reasonable numbers and we can extract the number of authors, correct for multi-affiliation, and then retrieve how much CO2 in tons per year should be associated with that. Okay, so we can also do that for other infrastructure, for example, for ships, very large research ships that goes for example, for the international drilling program. You have a very large ship, we can estimate its fuel, how much fuel is used during its days of operation, find a certain footprint, and then do a bibliographic search and find how much is it accounting in how much the geoscience lab is responsible for this emission. And so a summary figure here, you have the share of worldwide usage in per mil, and the infrastructure global footprint in kilotons of CO2 equivalent per year. And here each color for the triangles is a different lab of the institute in Toulouse. So, and you have typical satellite missions, because this is mostly satellites, are between 1 and 10 kilotons per year. You have the Pleiades mission, for example, or the JSON for oceanography, Venus for vegetation monitoring, Envisat, etc., and many others, MODIS. And then for the different labs, depending on how many scientists are using it and how many are publishing with it, we can estimate a total attribution that can be as low as 0.1 per mil and as high as typically 1 or a few %. And in yellow, I showed the data from the previous publication for astrophysics to show that we have some good consistency in the estimate of both attribution and footprint. So when we do that, if we basically look at all these data, sorry, let's go back one minute. And if we sum all the satellites that are relevant for a given lab, where any lab is publishing with it, we obtain, again, an emission in tons of CO2 that we can show in tons of CO2 per person. And you can see that I showed you for only 4 labs here, but if you look at these 2 laboratories, the laboratory of oceanography from space and of spatial studies on biosphere, it's in their names. They are very focused on remote sensing, and most of the research is done with remote sensing. They are actively developing many satellites, actually, with the French Space Agency and the European Space Agency. And you can see that therefore, the CO2 emission associated with the satellite is the first source. And it's between 7 and 11 tons of CO2 per person. So it's a really large amount, much more than all the CO2 associated with expenses or air travels. When you look at labs where satellite is a bit less predominant, like the meteorology lab or the geoscience lab, we obtain smaller values, but still in my lab, for example, it's about almost 2 tons of CO2 per person. And of course, this tons of CO2 per person is divided by the average lab, but it's mainly reflecting the fact that most people on these 242 persons are not doing research with satellites. And when we look at the total, what is striking is that we are between 10 tons and 23 tons of CO2. So these are really large when we compare to the target of decarbonization. To compare to other data, because this is unpublished work that I should submit hopefully before the end of the year, you can look at some other recent work. There is a report for the European universities in 2022 that estimated the tons of CO2 per employee. And what you can see is that, of course, if you look only at scope 1 and 2, or scope 1 and 2 and travel, you have emissions that are rather below or around 5 tons per CO2 per person. But when you look at universities that have gathered more extensively the scope 3, so looking at the different purchases over aspect, they are also above 10 tons per person and up to 30. So it's quite comparable. We have also what happens for labs in France with purchases, and that also are at similar value than what we found, 2 to 5, travels 1 to 2. And when you sum the different aspects, you also reach something like 6 to 8 or to 10 tons. One last aspect is that maybe you have noticed that in the carbon footprint that I showed, the heating and electricity was a very small part of the CO2 emission for France, but this is very strongly influenced by the fact that the electricity mix is very decarbonized in France. If you look at the CO2 footprint for astronomers from this recent publication also, in Germany, it's about 18 tons. And it doesn't account for satellite or purchases. It's flight, commuting, heating, and electricity. You can see that electricity alone is about 5 tons of CO2 per person. But if you look at Australia with a very carbon-intense electricity mix, actually you reach 25 tons just for the electricity of the laboratory. And when you sum everything, you are about 40 tons. So again, the value I present already can be quite inflated when the electricity mix is very carbon intensive. And before turning to reduction, I want to emphasize that on this question on infrastructure, we have some information on what is planned for the next decade for Europe. There are something like 18 new projects and 37 ongoing landmarks that will represent almost 20 billion of euro. And what you can see is that they are ranked here by different research discipline, let's say. So environment and earth science are here. You have physics and you have astronomy and social science, for example. And the construction is just already several millions of kilotons, especially in physics and astronomy. but environment is not so far. And the operation are also hundreds of kilotons, so about 1 million of tons of CO2 per decade of operation. And again, it's strongly dominated by physics. Whereas if you would like at social science, for example, you are much lower than many other disciplines. Okay, so this was a quick overview, and we can have some discussion after on what are the different sources and what is the level of CO2 emission by scientists. So now we can think a little bit to what can be done if we would want to reduce them. So looking again at two different budgets for my lab and for the lab of oceanography, you can see that solutions that are relevant to everyday life will have a relatively minor impact. Just because commuting or electricity or heat or meals that are not shown here, if you change the habits here, you will only reduce small fraction of the budget. Electricity is also a small question in France, but it can be more important to save electricity or invest in renewable electricity production to reduce the carbon intensity of what the university or the lab is consuming. But then the other targets, they will have to focus on air travel, purchases, or IT and infrastructure. So I will go a bit in turn on these points. One thing is, what can we do if we change our habits of flying? And there have been a lot of discussion on that, whether scientists are flying too much, why they are flying, for conference, for meeting colleagues, or for field work. But one recent work that is in review now is showing that based on a large database of French labs, what you can achieve as a reduction of the CO2 footprint of flying. This is what is shown in these different boxes. So up to 50, 60% and 0% if you do nothing. But what can happen if you put a limit on the minimum distance you can fly? So basically saying that if you are below 600 or 1000 kilometers, it's necessary to take the train rather than an airplane. This would reduce by a certain amount, up to 20%, if you put a relatively large threshold of more than 10 hours of train. And then the other axis here is showing what happens if you impose quotas on flight. So there are many different flavors of quota if you want. You can reduce the mileage, you can reduce the number of travel, or you can limit only certain type of travel, like the one to conferences, etc. And if you do that, you can also achieve up to 30, 40%. And in combination, this can be up to 60% reduction of the travel footprint. So it's really significant, but this requires to really change the way we are traveling for scientific purposes. Another aspect is on the reduction of the footprint of purchases. And this is another work in review also, with the same database of French lab that has been analyzed. And they show here for science and technology studies. So this is our domain. This is for social science, and this is for health science, life and health science. But what you can do is various type of measure shown by color here. And in order, they are related to basically buying less, either by extending lab equipment life, so renewing it less frequently, by pooling lab equipment between different labs or different institutes, replacing 80% of plastic by glass, imposing that all the food that is bought by the lab is rather vegetarian, reducing furniture purchases, IT, or reducing consumable. And if you put all of this together, you are nearly reaching 50% reduction of the purchased CO2. And the main points are reducing, buying less IT equipment, buying less consumable, and extending life, the lab equipment life, or pooling equipment. These are the way to really reduce our footprint. But again, this call into question how we organize a lab to do that, and what type of science we'll produce if we apply this type of constraints. For IT, I admit I was less familiar with this, but I found there is a very interesting, there is a team in the UK that has worked on that with Loïc Lanlong and other colleagues. And I show just some papers here where they present a green algorithm that allows to test how much carbon should be associated with the computation of your code. So you can send your code and do some tests on their platform, depending on your electricity mix, depending on how many times you run the code, etc. They can give you estimates. the CO2 and whether you can improve it. And then also they propose various rules to make the computing more sustainable. And of course, two things that they propose that could be applied not only to computing, but to any use of scientific resources is to calculate the carbon footprint of your work and to include the carbon footprint in a cost-benefit analysis. So when you want to do when you want to acquire new data, when you want to launch a new satellite, or if you want to do a new mission, a field mission, how much will it help your science and what will be the expected benefits compared to how much carbon it will emit? And then there are more practical advice, like, of course, keep, repair, and reuse devices to reduce the footprint of production. Choose your computing and storage facility based on the carbon mix. If you do your storage in France or Norway or in Australia, it will be very different. And then increase the efficiency of the code and be a frugal analyst. So I let you find more detail on this in the paper there. Before finishing this little part, I want to show also that all these things are not just wishful thinking, and there are some laboratories, at least in France, and you know maybe examples in your own countries, that have started to implement that. You have, for example, the case of the Geoscience and Environment Institute in Grenoble, that is with more than 300 researchers, so it's a relatively large laboratory. And in 2019, they had a prospective workshop where they thought of how they could meet the IPCC target, the idea that in the next decade, the IPCC recommend that we halve CO2 emission to follow the Paris Agreement. This is a global average, but they try to do at least that. And they proposed and adopted a manifesto. They voted some strategy by the lab board, and they started to perform repeated evaluation of their CO2 footprint. And you can see that then they try to reduce every year by 10% the amount of CO2 they emit by discussion among the team, but also, for example, by setting CO2 quotas on professional travels. So each of the different teams in the lab has to discuss and limit their travels to a maximum amount of CO2. And so far, we are following the trend here. Okay, this was some example for this more standard, not standard, but let's say for what you can do inside your laboratory, because this is at hand. There is a question of how you perform science, with what equipment, with which travels. But the question of infrastructure is a bit less tractable, because typically the infrastructure are decided by large consortium, by international cooperation, etc. And what is important, if you look at the weight of infrastructure, this is showing here the potential of CO2 reduction. If you apply different things, you reduce electricity, you reduce IT purchases, you install flight quotas, you reduce purchases, etc. And this is for the different lab in Toulouse. You can see that we can reach reduction that are about 40%, 50% of the local CO2 footprint. But if you include the footprint from the infrastructure, from satellites, and from overground infrastructure, this is drastically reduced, and you drop to 15, 20, 30% for many labs. So there is really a question of how do we account for that? And I have no clear solution here, but clearly there is a question of the community must be aware of the impact. So it's important to discuss and maybe make community statement, include the greenhouse gas estimate in infrastructure planning when you want to decide for a new satellite mission or for increasing or renewing some infrastructure. And again, weight the community service in terms of impact and benefits. And more broadly, also because all what I show can have a very strong impact in how we organize science, there are really questions that goes back to the question of slow science, in a sense. What can we do if we want to account for the planetary limits in the academic system and in the broader society? Because you can make the point that if scientists are not able to reduce their CO2 footprint, it will be, whereas they are informed, they have certain freedom in how they work, and they are supposed to be a public service also. There are strong questions of how industry or average citizen will be able to adapt. So I think we have very strong reason to try to be at the forefront. And there are many questions that we can ask. And I recommend the reading of this interesting paper in 2023 from Urai and Kelly that is called Rethinking Academia in Time of Ecological Crisis. And there are questions of what is the place of society, what is the role, sorry, of science and its place relative to society. Are we studying society as an external player, or are we embedded inside society and the planet? And this call question, for example, in how much time do we spend in doing research, how much time do we spend in engaging publicly in the media, in supporting citizen organization or NGOs. There are questions on how we collaborate with the industry, or also how we organize our funding system and how we study our methods and impact, or rather, because as you may know, in social science, there is a lot of time that is devoted by scientists to develop reflective studies that actually look into what they are doing, whereas in earth science and natural science, we are much less used to spend time on that. There is question of the competition of the rat race, as we can say, versus slow science. How do we change our institution to decrease this competition, to make it meaningful, and to be sure that we have time to also invest in other activities, engagement, reflexive science, transdisciplinary projects. I have shown you before on this big diagram for the infrastructure that social science infrastructure are much less, are spending much less resources to be developed, and most social scientists are used to produce knowledge with very small amount of resources. And there are questions of how maybe we can join transdisciplinary project with them, spending more time. Of course, it has a cost in terms of time, but it may require less machine, less equipment, and more human resources. There are also questions on how to collaborate differently with scientists from the global south to be more inclusive, to relocate your fieldwork, to be able to work on some data that is from the other side of the world without necessarily going them to pick them up. And of course, again, I want to say that all what I'm saying today is not something, it's not just a reflection. It can be, you can go from belief to action if you think this is important, by spending time on thinking on what is your academic and professional goal and values. Maybe putting aside some bullshit work, we can discuss on that, but there are sometimes things that keep us busy that we may criticize in the academic system. And then try to secure some time every week. And many things can be done, setting up a reading group, discussing key paper on the crisis, its cause, its solution, and the role of academics. We can also spend some time by adding some slides in our lectures or in our talks, even if it's not the topic of the talks or of the lecture, but adding slides on climate and biodiversity crisis to open up new conversation, to raise awareness. And then there are, of course, the question of joining a group, either a sustainability community that is trying to reduce the footprint of scientific activity in your university, in your institute, and trying to change maybe the way we work, trying to lobby the direction or to make proposition. And then there are also questions on joining local or national or academic climate action groups. And there are some examples here: Scientists for Future, Scientists Rebellion, Faculty for Future, etc., that also promote this type of activities. Okay, I don't know where I am in terms of time. There is a wrap-up slide here just to say that when you look at emission from Earth and Space Science Lab, you find really large 10 to 20 tons of CO2 per person per year just for professional emissions. So scientific activity has important climate impact, or if you want, it has a footprint that is above what we would term sustainable. And it's dominated by infrastructure when they are used, so satellite for remote sensing lab, and expenses and travels. And therefore, we have to think beyond simple reduction in terms of, we cannot just save electricity or save water or recycle the plastic, because these aspects are relatively small in what we do actually, and more impacting measures require scientists to limit or to adapt to some extent their activity. Question of flight quotas, reducing purchases, limit the size and the number of new infrastructure. And again, to do that, we may want to need or to frame this into a bit of reorganization of the goal of science, and moving maybe toward a form of slow science. At least that's what I would advocate. And this could allow to change research topic, to relocate fieldwork, to try to work more on interdisciplinary topics with social sciences and spend more time engaging with society. And in the last years, I can say that I have been following these three lines of these three aspects to various extent. And you can still continue to do some science, but of course you need to be able to drop the competition, because this different aspect will take time off standard expertise in geomorphology if you are a geomorphologist. But of course, I want to say as a last word, if you are interested in this type of aspect, if you think it's important, if you want this to be part of your professional time, of your professional work, it's essential to join a group. I put some French group here, but there's some national group, as I said, or local group in your university, just to be able to work collectively and to get some motivation, ideas, and to be in a nice dynamics. Thank you for your attention.
Brilliant. Thanks so much, Odin. That was a really, really thought-provoking talk. I'm going to be thinking about that for a long time over the next few days. If anyone has any questions for Odin, please feel free to drop them in the Q&A. I can see a couple there already. So I'll just read them out. So the first question, I think, is about the first part of your talk, Odin. Saying, does the decoupling graph take into account offshoring of emissions?
Offshoring, you mean the import and export?
Jamie, if you're there, do you want to either unmute yourself or type in the chat?
Yeah, sure. Sorry, it was just it was about the green growth section of the talk. You were talking about high-income countries had decoupled their growth from emissions. And I was just curious as to whether that included emissions that were now sort of on the balance sheet of other countries, if you like.
Yes. So you mean, for example, the fact that you have to produce a footprint by accounting for the importation, for the
exactly,
for the goods that you consume. I think it does. My view is that I think it does. And the point is that that's why you have a very small decoupling, and it actually happens for only a few countries. I don't remember the name of the countries. You need to check the country. And it's on average time. It's with a smoothing average, and it doesn't account for the COVID period because there was a recession for most of this country at the time. Yeah.
Great. And the next question is from Adina, and she says, your presentation is pointing out that the computing and fieldwork tasks contribute to the majority of our kind of professional carbon footprint. How could we expect emissions to evolve if we include psychologists and social scientists in our projects, considering that they also involve fieldwork and lab experiments? So is there a way we could redesign our research that would reduce kind of all these efforts or reduce our computational efforts?
Yes, so of course, when I mention that we can do interdisciplinary projects, it means that we don't drag social scientists to analyze or perform very large computing centers, but rather the opposite, that we take time and we invest into producing knowledge and science that do not require to go on distant field work or to do large modeling or to use satellite data, but rather to go on a small scale and low tech or low resources project that can be typically done with social scientists. And I can give a concrete example, which is that recently I have been working with a colleague that is a risk sociologist, a natural environment and risk sociologist. And we went to a landslide, a slow-moving landslide in the Pyrenees. So this is very close of Toulouse. And the project that we did with different students, and we are now trying to write up a paper, was mainly based on interviewing residents, mayors, experts that have been working on that. And therefore, producing and addressing the knowledge gap, not of how the landslide is moving. There are other colleagues that I know personally that work on monitoring the landslide, but on working on what happens and how do we help the people facing the risk, and what are the social and psychological issues in risk management rather than hazard management by monitoring the landslide. And doing that, I compare to flying to Nepal and using satellite data and models to map landslides, for example, in Nepal, this would have a very different carbon footprint.
Great, thank you. The next question is from Bastien. He says, thanks, Odin, for this great talk. How can we meet the right balance between the need for transparency and data sharing to ensure people can reproduce our study while reducing our carbon footprint in terms of storage?
Yes, one option, like it's true that if we want to, for various applications, there is a sense of replicating, saving, storing the data. I think here it's useful to go and look at exactly here at this website, and there are some other papers and other pages on this website, but they argue one point, for example, is choosing the storage facility. Again, if you store on a cloud or on a facility that is in France or in some relatively low carbon footprint in Europe, rather than in a cloud in the US, you will have a different footprint. Another thing is to be careful for zombie data, as they call. So the fact that sometimes we tend to not be very rational in what we save and how. So this could be an effect, but beyond that, for storage and for open transparency, I admit that this is something that may continue to grow. What I would slightly turn on the question and say, as it was said for the big data in the talk of Julia, in some fields we can see that we are the speed at which we accumulate data is much faster than the speed at which we can analyze it and interpret it. And this is very suboptimal because we invest a lot of resources into producing data, into storing it, but we are far behind in terms of human resources to analyze it. So here I have no clear solution beyond the fact that maybe we have to think also in terms of what are the infrastructure producing the data and whether or not we really need more data for this question.
Yeah. Okay, so our next question is from Lester. Yeah, he's a really good point. He says, again, great talk. Coming from the global south, so Chile, I think a lot of governments in the global south push exactly in the opposite to what you've mentioned in the talk. So, part of succeeding, I guess, in science is being asked to get new equipment, to go to international conferences, to build new labs. So how can, I guess, we work on changing those perspectives?
And it's not only true for the global south. I agree that the global south maybe is trying even harder to catch up with the global north. That is some form of advance or some form of advantage. But it's also true, the same question could be put in terms of career stage, because when we are a PhD or a postdoc, we are pushed to be excellent and highly productive to get a position because of the competition for having access to a position. And yeah, I agree that it's clearly a problem. It goes back to the general problem of, in a society of growth, there is a contradiction between growing and between reducing the amount of resource that we consume or of pollution that we produce. And so there is no, let's say, I can't have a direct, easy answer. It depends if you are permanent or precarious scientist, or permanent or non-permanent contract. It depends at which scale you want to discuss. But I think at least there is a difference between scientists and some other professions, let's say, that scientists have a relatively large autonomy in defining on what they work, how they define new research projects, and etc. And therefore, they can maybe try to self-organize and push up some ideas and some proposition in terms of slowing down, in terms of changing the criteria. There are tiny progress in this direction, in the sense that many organizations, for example, propose to be a bit more qualitative and less quantitative in the evaluation of researcher or in the recruitment, to include more diversity or other original profiles, to include more community service. We could push for the fact that in recruiting and in promoting scientists, the question of engagement towards society, in how we diffuse our knowledge, how we train the great public, how we maybe interact with politicians, policies, NGOs, this could be recognized more. All of these are different targets, and I am very well aware that it's not necessarily in the agenda of the different institutions, not even in the global north. But I think, yeah, if we are aware of the problem and if we take it seriously, we should devote some time to try to push in this direction. And as I was saying, we cannot push alone. So the question is like, is there a group? Is there some group that have reorganized their research? Is there some association of scientists that are proposing to interact with policy leaders or with the great public, etc.? Joining such groups can be a first step to think and to clarify what are the different options depending on your career stage, depending on your countries, depending on the amount of funding that you need, etc. But clearly there is a contradiction with the basic incitation that would be produce knowledge, and if you need to produce new knowledge with resources, just ask for resources and use them.
Great, thank you. Yeah, we then have a comment from Ian Evans. So he says that, you know, clearly research in places like Antarctica is really vital for understanding the effects of climate change. And there's a lot we can do with remote sensing. As you mentioned in the talk, that this also has a big carbon cost, but some of it can really only be fully understood if scientists travel there with a great carbon expense. So yeah, I guess it's just the contradiction there.
Yeah, I can do a nice quick anecdote on that. Is that this lab, the lab I showed, the lab that I showed here, the lab in Grenoble, actually has several researchers that are working in the polar region and in Antarctica or Greenland. But they still manage to have an exemplary trajectory. And as the person, it's one of the director of the lab that sent me these graphs. He was saying that because they were on a budget by team, if a team is specialized on Antarctica, they can still discuss how to maintain some field work there, but they will have to shrink more what they do in terms of modeling or in terms of over experiment. And some other teams that are specialized in modeling, they will still keep a lot of space for CPU and for high computing, but they will reduce more the amount of flight that they do for conference and etc. So yeah, I think there are two points maybe that I can make is that we have to be aware that the different form of activity produce pollution in a sense. Either if you're an experimentalist, you buy a lot of machine. If you are doing a lot of field work, you fly more. If you don't do any of this, but you use satellite data, well, somehow the satellite was built for you and launched for you. So the question is how we can reduce. I'm not asking I think the point of exemplarity is not to say that we should stop science tomorrow, but is that we should try to be on a reduction curve. And this reduction curve is a few percent. It's not negligible at all. It really requires to think and to make effort. But yeah, again, if like you know, there is this classic paper on the different arguments to delay or to deny action for climate change. One of them is to always say, well, we are only a small part. Why should we start us? Well, if we all apply this thinking, of course, nobody. There is not one person emitting half of the CO2 of the world. Everything is distributed on many different activities, many different reasons. Actually, there is reason to think that scientists could reduce more of their activity than agriculture or health production, because we maybe want to keep more hospital than researcher, or we want to produce food at certain expense. So being aware of that and having some autonomy and flexibility, I think we have to show exemplarity and therefore reduce progressively. But we can keep some type of research. We can judge that some satellite mission is really essential and some other are less, and progressively reduce our footprint like that.
Great, thank you, Odin. Lots of food for thought there. There's a few more questions. I think we'll probably leave them for now just because we're kind of running into our break time. Yeah. But maybe you can take a look and just discuss with people in the chat. So some questions about what we mean by slow science and about other practical steps that we could take, which we can discuss when we have our discussion session as well. Great. So let's
Thank you.
again give Odin a virtual round of applause if we can for such a great talk.